So this is going to be a video explanation of question number 5 from problem 6, which regards entropy and how you can get absolute entropy from measurements of heat capacity. So the question is, scientists wish to measure the absolute value of entropy of the system. So let's take a look at this term, absolute value of entropy. So the absolute value of entropy is the entropy change from 0 degrees Kelvin to a specified temperature, which we'll call T2. And the third law of thermodynamics states that this term here equals 0. That's a definition that allows us to provide a scale to entropy. Okay, so now we know what we're looking for, but how can we relate entropy, a change in entropy, to the heat capacity? Let's take a look at our definitions of entropy. We have first the thermodynamic, then we have the statistical definition, and then from the statistical definition with Stirling's approximation, which requires large amounts of molecules, you can get the probabilistic. So which one of these is going to be the best? Well, considering we're looking at heat capacity, how about a change in heat? So let's see if we can derive a relationship between heat capacity at constant pressure and a change in the amount of heat taken up in a reversible process. This is what that Q rev is. So we have heat capacity at constant pressure is equivalent to the change in enthalpy divided by the change in temperature, and that is at constant pressure. And let's take a look at our definition of enthalpy to see if we can somehow relate that to heat. So heat enthalpy equals the energy of a system, defined in all state variables, plus pressure of the system times its volume. A small change in enthalpy is going to be the small change in energy plus pressure times the small change in volume, plus by the chain rule, small change in pressure times the volume. And since we have defined that there's a constant pressure, there's no change in pressure here, so that term goes to 0. So we can say that enthalpy, change in enthalpy, is equivalent to a small change in energy plus P dV. Now let's see if we can get that related to heat. So we also know that the change in the energy of a system is equivalent to the amount of heat taken up plus the amount of work done on it. Okay, and we can rearrange this to get it in terms of heat, which is what we will be measuring in heat capacity. And if we assume all the work being done is expansion work, we can say dq equals negative, keep track of the signs here, this is the external pressure, times dV. We had to put a negative sign here because we want to keep the dW positive if there is work being done on the system, which would have a negative dV. So from this, we can see that dq generally equals du plus p dv. And you could see that these are equivalent here, thus showing us that the change in enthalpy equals the change in heat under constant pressure conditions. Great. Now we can relate our heat capacity term which is the change in enthalpy for a given change in temperature, to the amount of heat taken up by a system. So that is going to be dq over dt. And then that allows us to relate the heat capacity to the entropy change. So this thermodynamic definition of entropy is usually written like this, but what this term is actually the heat transferred during a reversible transition. So it's actually a change in the heat of the system, so the final minus the initial. So it's actually a change in heat. So equivalently, you can rewrite this as delta S equals delta Q under reversible conditions over T. And if we write that in differential form, we can say that ds equals dq over T. Great. So taking our heat capacity equation, our new definition of it, we can say that the change in entropy of a system is equivalent to Cp dt over T. Because of this, you can rearrange dq equals Cp dt. And that goes in right there. All right, great. So now we have an equation relating the change in entropy to the heat capacity at any given point. So if we want to get the total change in entropy between 2 points, we just integrate this equation, Cp dt over T, and that's going to be between 2 different temperatures, T1 and T2, and that's a general equation to get the change in entropy between any 2 temperatures of a substance. But if we want to get the absolute change in entropy, we're going to have to go from 0 degrees Kelvin to our temperature of interest. So the absolute entropy equals integration from 0 to T2 over Cp T dt. And the way this is experimentally worked out is you will, across a range of temperatures, you will measure the heat capacity, and you'll get this interesting graph here with a bunch of different points. And you usually can't actually measure it all the way down to 0. So what you'll do is you'll just extrapolate and get this portion of it. And then from those measurements, you can scale it by T at every single point and get a slightly different graph. And then if you integrate underneath this, this will give you your absolute entropy at a given temperature, T2.